Hello everyone. Today I am here to make a audio recording on the chapter non-aqueous solvents. Most of the chemical reactions are carried out in solutions and the behavior of substances also depends upon the nature of the solvent. In the earlier days of development of chemistry, the reactions have been carried out only in one solvent, namely water. It has been facilitated by its ready availability, ease of purification, together with its favorable physical and chemical properties such as long liquid range, high dielectric constants, specific heat, heat of volatilization, dipole movement, etc. Water is neutral, odorless, non-toxic and non-poisonous. It can therefore be handled safely. The properties of water make it an excellent and useful solvent for a large variety of substances. In fact, the excellent properties of water have hindered the development of non-aqueous solvents. The solvents other than water which are used for carrying out chemical reactions are called non-aqueous solvents. Attempts have been made to find some other substances which could behave as good solvents like water. Organic chemists have been using many solvents such as benzene, carbon tetrachloride, acetone, ether, etc. for dissolving organic compounds which are insoluble in water. Now there are many other solvents available, for example liquid NH3, H2SO4, liquid HF, liquid sulfur dioxide, etc., which have been frequently used. In the present unit, we shall discuss briefly the important features of non-aqueous solvents such as ammonia and sulfur dioxide. Now, physical properties of solvents and their role in chemical reactions. The usefulness of a solvent is determined from its some specific properties that may help to carry out the chemical reaction and separate the products more conveniently. Some of the important physical properties of the solvents are discussed below. Melting point, melting point and boiling point liquid range. The melting point and boiling point of a solvent determine the temperature range within which can exist in the liquid state under atmospheric pressure. Since most of the reaction in a solvent system are carried out in liquid phase, the melting and boiling point give the temperature range within which the solvent is useful. The melting and boiling point for some common solvents are given in table like H2O 0.0 to 100, NH3 minus 77.2 minus 33.4, sulfur dioxide minus 75.5 to minus 10.2. It is clear from the above data that the water has excellent liquid range from 0 to 100 degrees Celsius. At ordinary temperature and pressure, acetic acid can also act as solvent at ordinary temperature, while ammonia and sulfur dioxide can act as solvents only at low temperature. Heat of fusion and heat of vaporization. The value of heat of fusion and heat of vaporization help to know the nature and strength of forces which hold the molecules of the solvent together in the solid or the liquid state. As we know, the amount of heat absorbed by 1 mole of a substance to change from solid to liquid state is called its molar heat of fusion. Similarly, the heat absorbed by 1 mole of the substance to change from liquid to vapor state is called its molar heat of vaporization. Larger the value of heat of fusion or heat of vaporization, the stronger the intermolecular binding forces in a solid or the liquid respectively. Therefore, the magnitudes of molar heat of fusion and molar heat of vaporization give us some insight into the nature and strength of the intermolecular forces, and this also determines the solvent properties. A better idea of the intermolecular forces in a solvent obtained by the ratio of molar heat of vaporization to the boiling point. This ratio is also called Proton constant. For normal liquids, if molar heat of vaporization are expressed in calorie and boiling point in constant is about 90 for normal liquids, such liquid exist as independent molecules without any bond between them. A higher value of proton constant indicates associated molecules. For example, common solvents like water, ammonia, hydrogen fluorides have proton constant value greater than 21.5 and are therefore associated liquids. The molecules of these liquids are polar. The charge ends of the molecules come nearer is due to their tendency to orient themselves so that the oppositively charged end of the molecules come nearer to each other. The inspection of table shows that the value of molar heat of fusion for water and ammonia are almost same. This means that the force which hold molecules together in water and ammonia are of same magnitude. Dielectric constant. This property is a measure of the polar nature of the solvent and helps to estimate the solubility of a polar or non-polar substances in the solvent. Now, according to Coulombic law, the force of attraction between two charged ions is given by F is equal to Q plus Q minus upon E R square, where Q plus and Q negative are the charges of the cation and anion respectively. R is the distance between them equal to the radii of the ions is a constant called the dielectric constant of the solvent. If E is large, the force will be small. As a result, only a small amount of energy will be required to separate the ions and it will be easy to dissolve an ionic substance. Thus, in solvents of high dielectric constant, the ionic substances will dissolve readily. With the decrease in dielectric constant, the solubility of ionic compounds will decrease. The dielectric constant of some common solvents are given in table. H2O is equal to 81.7, ammonia is equal to 22.0 and sulfur trioxide is equal to 17.3. It is clear that solvents like hydrogen fluoride and water are good solvents for ionic and polar compounds because their high electric constant values. On the other hand, solvents like ammonia and sulfur dioxide with small values of dielectric constant show decreased tendency to dissolve ionic compounds and especially those containing multi-charged ions. For example, carbonates, sulfate and phosphates are partially insoluble in liquid ammonia or liquid sulfur dioxides. Dipole moment. The dipole moment is related to the dielectric constant of the solvent. An ionizing solvent has large dipole moment and also has a large dielectric constant. It is related to the polarity of the bond in the molecule. Greater the polarity of the bond in the molecule, larger is its dipole moment. Solvents having high dipole moments have greater tendency to dissolve the polar or ionic substances. This is because of the fact that the greater polarity results in strong bond between the solvent and the solute molecules and larger solvent energy is released. This large solvation energy is sufficient to overcome the lattice energy in the solute molecules and helps in dissolving the solute. Viscosity. It is a measure of the fluidity of the solvent. Solvents like water, ethyl alcohol, and carbon tetrachloride have low viscosity and are highly fluid and flow rapidly under ordinary temperatures. On the other hand, anhydrous sulfuric acid and high molecular weight hydrocarbons have high viscosities and flow at much lower rates at ordinary condition. In solvents of low viscosities, the operations such as precipitations, crystallizations, filtration, etc. can be easily carried out without any difficulty. With increase the viscosity of a liquid, increases the difficulty of such operations. Now, type of solvents. Non-aqueous solvents has been classified in many ways. The following are the important classification based upon the chemical properties of the solvents. Protonic and non-protonic solvents, acidic, basic or amphoteric solvents, ionizing and non-ionizing solvents, coordinating and non-coordinating solvents. Protonic and non-protonic solvents. The solvents from which proton H positive ions can be derived are called protonic solvents. Therefore, protonic solvents contain ionizable hydrogen. Common examples are water, hydrogen fluoride, sulfuric acid, and hydrogen cyanide. The solvents from which protons cannot be ordinarily derived are called non-protonic solvents. These are also called aprotic solvents. In other words, these solvents do not contain ionizable hydrogen atoms. Common examples are sulfur dioxide, benzene, carbon tetrachloride, etc. Acidic, basic or amphiprotic solvents. This classification is based upon the acidic or basic behavior of solvents. The solvents which have a strong tendency to donate protons are acidic in nature and are called acidic solvents or protogenic solvents. For example, H2SO4, liquid hydrogen fluoride, acetic acid, etc. Solvents which have strong tendency to accept protons and are basic in nature are called basic or protophilic solvents. For example, liquid ammonia, pyridine, hydrogen, ethylene diamine, etc. These solvents, which neither have a strong tendency to gain nor a strong tendency to lose protons, are called amphiprotic or amphoteric solvents. In other words, they neither behave as strong acidic nor basic but can behave as acidic as well as basic depending upon the nature of the reacting species. For example, water, ethyl alcohol, methyl alcohol, etc. Ionizing and non-ionizing solvents. The solvents which are capable of undergoing self-ionization or auto-ionizations are called ionizing solvents. Some common examples are water, ammonia, hydrogen fluoride, sulfur dioxide, etc. These ionize as shown below. These solvents are generally polar or ionic in nature. On the other hand, the solvents which do not ionize at all are called non-ionizing solvents. Some common examples are benzene, carbon tetrachloride, hydrocarbons, etc. These are non-polar or non-ionic in nature. Coordinating and non-coordinating solvents. The solvents which are capable of coordinating with the metal ions or anions of the solute are called coordinating solvents. For example, ammonia, sulfur dioxide, dimethyl sulfoxide, acetonitrile, dimethylformamide, nitromethane, etc. On the other hand, the solvents which are not capable of coordinating with the metal ions or anions of the solute are called non-coordinating solvents. For example, carbon tetrachloride, saturated hydrocarbon, etc. These are not of much interest to inorganic chemists. Types of reaction in non-aqueous solvents. The following types of reactions commonly occur in non-aqueous solvents: metal theoretical or precipitation reactions. The reactions in which precipitations occur on mixing two solutions are called metathetical or precipitation reactions. These type of reactions can be predicted if the values of the solubility products of the compounds formed in the solvents are known. These values depends upon the nature of the solvent used. For example, in water, silver nitrate and barium chlorides react to give a precipitate silver chloride, leaving barium nitrate in the solution. On the other hand, in liquid ammonia, a precipitate of silver chloride combines with the barium nitrate to give precipitate of barium chloride, leaving silver nitrate in solution. Therefore, reversal of a chemical reaction takes place on changing the solvent. Similarly, sodium hydroxide is highly soluble in water, but it can precipitate it in liquid ammonia. Water soluble copper sulfate may be precipitated in anhydrous acetic acid. Salt formations. The reactions between appropriate acidic and basic substances to form salts are called salt formation reactions. In such cases, the solvent used must be one in which the appropriate acids and base can exist. For example, sodium ureide cannot be prepared by the reaction of urea on sodium proton on sodium hydroxide in water. It is because the strong base available in water will not take a proton from urea molecule. In other words, the sodium salts of urea is unstable in water and ureide ion will take a proton from water to form hydroxide ion. However, this salt can be easily formed in liquid ammonia solution by the reaction of urea with the strong base soda amide to give sodium ureide plus ammonia. Acid-base reactions. The acid-base reactions in non-aqueous solvents can be explained on the basis of solvent system concept. As already learned, according to solvent system concept, an acid is a substance that by direct dissociation or reaction with the solvents gives the cation characteristics of the solvent. Similarly, a base is a substance that gives the anionic characteristics of the solvent. The acid-base behavior of a substance depends upon the acid-base nature of the solvents, the character of the solute, and the solute-solvent interactions. In the case of protonic solvents, cation is the solvated proton and the Bronsted protonic concept is same as the solvent system concept. For example, in liquid ammonia solvent, NH plus 4 ion act as base and NH minus 2 ion act as bases. The neutralization reaction is acid plus base gives salt plus solvent. In non-protonic solvents such as benzene, carbon tetrachloride, Lewis Acid-base type of reactions can occur because of non-ionization of the solvents. The acid-base behavior of a solute in a solvent depend upon the acidity or basicity of the solvent. For example, acetic acids behave as strong acid in ammonia, weak acid in water, but a base in sulfuric acid. Solvolytic reactions or solvolysis, the reaction in which the solvent molecules react with the solvent in such a way that the solvent molecules split up into two parts, one or both of which get attached to the solute molecules or ions, are called solvolytic reactions. Since these reactions occur through self-ionization of the solvent, the concentration of either the cation or the anion is changed. For example, the solvolytic reaction in water, ammonia and ethanols are given below. Water as solvent. H2O gives H3O positive plus OH negative ion. SO2Cl2 plus 4H2O gives SO2 twice OH plus 2H3O positive plus 2Cl negative. F negative plus water gives hydrogen fluoride plus hydroxide ion. Ammonia as solvent. 2 moles of ammonia gives ammonia cation plus ammonia anions. SO2Cl2 gives 4NH3 gives SO2 twice NH2 plus 2NH4 positive plus 2Cl negative. H positive plus NH3 gives NH negative 2 plus H2. Alcohol as solvents. Alcohol gives alcohol cation and anion. SO2Cl2 plus alcohol gives SO2 twice OC2H5 plus 2C2H5 OH2 positive plus 2Cl negative. CH3 plus 2 alcohol gives OC2H5 negative plus CH4. It may be noted that in case of solvents like water, ammonia, alcohol, acetic acid, etc., the term hydrolysis, ammonolysis, alcoholysis and acetolysis are used respectively. Solvations, the reaction in which the molecules of the solvent get attached to a solute species, cation, anion or molecules are called solvation reactions. The species formed is called solvate. The solvation reaction in water, ammonia, alcohol, etc. are called hydration, ammoniation, alcoholation, etc. and the resulting solvents are called hydrates, ammoniates, alcoholates, etc. Solvation of a cation occurs through ion dipole interaction between the positive cation and the negative end of the dipole, or through coordinate bond in which the solvent molecules donate a pair of electrons to the cation. On the other hand, solvation of anion occurs through ion dipole interactions between the negative ion and the positive end of the solvent dipole, or through hydrogen bonding in case of solvents such as water, ammonia or hydrogen fluoride. It may be noted that in certain cases it is difficult to distinguish between solvation and solvolysis because in many solvolytic reactions the first step consists of solvation reactions. However, the term solvation is used for those reactions in which the solvent molecules remains in the resulting products. Let us discuss some reaction in two common non-aqueous solvents. Liquid ammonia. Liquid ammonia is one of the most extensively studied non-aqueous solution. It is now used as a highly useful solvent and a reaction medium for many types of organic and inorganic synthesis. Its most of the physical properties resemble those of water. Comparison of properties of liquid ammonia and water. The comparison of properties of liquid ammonia and water reveals the following parts. Liquid range. The melting and boiling point of liquid ammonia are lower than those of water. In liquid ammonia, the liquid ranges from minus 77 to minus 33 degrees Celsius and therefore it presents some handling problems. Therefore, some precautions have to be taken while using liquid ammonia as a solvent. It is generally handled in cooled vessels, and nowadays a wide range of techniques have been advanced for handling it. Hydrogen bonding. Like water, liquid ammonia is an associated solvent through hydrogen bonding because it contains a strong electronegative than oxygen and therefore NHN bond is weaker than OHO bond. As a result, the freezing point and boiling point of ammonia are less. Since ammonia is less associated than water, it is a better solvent for organic compounds. Dielectric constant. The dielectric constant of ammonia is lower as compared to water, suggesting its lesser tendency to dissolve ionic compounds. Liquid ammonia is therefore a poor solvent for ionic substances. Soluble salts include most ammonium salts, nitrates, thiocyanates, and iodides. Fluorides and many oxysalts are generally insoluble. However, ammonia has lower viscosity than water, and this might be expected to promote greater ionic mobilities and thereby compensate to some extent for the effect of dielectric constant. Self-ionization. Both ammonia and water show comparable self-ionization as represented below. However, the extent of auto-ionization of liquid ammonia is less than that of water. This is clear from its low specific conductance and lower ionic product. Therefore, ammonia can conduct electricity to a feeble extent. Ammonia is a better solvent than water. The following properties of ammonia make it better solvent than water. Liquid ammonia is a very poor conductor of electricity. The specific heat of ammonia is more than that of water. Liquid ammonia is less viscous than water. Most salts, when dissolved in liquid ammonia, conduct electric current better than in water. This is not due to ionizing power of ammonia but due to low viscosity, which greatly increases the mobility of the ions. Liquid ammonia has high critical temperature and pressure. It is less associated than water and therefore is a better solvent for organic compounds. Liquid ammonia forms strong reducing metal ammonia solution with alkali metals. Therefore, it is an excellent solvent for many reduction reactions. Reactions in liquid ammonia. As mentioned earlier, ammonia has water-like properties as a solvent. It is therefore expected that the reactions which take place in aqueous solutions can also occur in ammonia solutions. Some of the important chemical reactions occurring in liquid ammonia are given below. Acid-base reactions. The acid-base reactions in liquid ammonia can be easily understood by comparing the reactions in water. According to solvent system concept of acid and bases, the substances producing hydronium ion in water act as acid while those producing hydroxide ion act as basic. Liquid ammonia ionizes as NH3 gives NH plus 4 or NH minus 2. Therefore, the substances producing ammonium ions in liquid behave as acid while those producing amide ions behave as bases. For example, ammonium salts such as ammonium halides, thiocyanates, nitrates, and soluble in liquid ammonia behave as acids. Similarly, amides, imides, and nitrites behave as the bases in liquid NH3. Therefore, the commonest base in liquid ammonia is potassium amide, which ionizes as KNH2 gives K positive and amide ion. Lithium amide, sodium amide, and alkaline earth metal amides have a very low solubility and therefore KNH2 is the commonest base in liquid NH3. Protolysis. Certain compounds like urea, acetamide, sulfamide, etc., which are incapable of donating protons to water, can readily donate protons to liquid ammonia. These reactions are called protolysis reactions. Hence, these compounds act as acids in liquid ammonia. Sulfamic acids behave as a dibasic in liquid ammonia. Sulfamic acid behaving as dibasic in liquid ammonia. However, it behaves as a monobasic in aqueous solution because NH2 group cannot donate a proton to water. Sulfamic acid behaving as a monobasic in aqueous solution. Acid-base neutralization. In aqueous solution, the process of neutralization of a strong acid and a strong base involves the combination of hydronium and hydroxide ion to form practically unionized water. For example, the neutralization of hydrochloric acid and sodium hydroxides may be expressed as this. In a similar way, the neutralization of an acid and a base in liquid ammonia involves the combination of ammonium and amide ion. There are many examples of amphoteric behavior in liquid ammonia. The compounds that dissolve both in acids and bases are called amphoteric substances. For example, in liquid ammonia, zinc amide shows amphoteric behavior analogous to that of zinc hydroxides in aqueous solution as a base. Thus, acid gives ammonium ion and bases give amide ions in liquid ammonia. These are termed as amino acids and amino bases. Reactions of amino acids. Amino acid is a substance that furnishes ammonium ion in liquid ammonia. Ammonium halides, nitrates, or cyanides are very soluble in liquid ammonia. Given ammonium ions and their concentrated solution act as amino acids, we note that acids gives hydrogen with metals in aqueous solution. In a similar way, the amino acids react with alkali and other metals to give hydrogen. A saturated solution of ammonium nitrate in ammonia also dissolves many metal oxides similarly to their behavior in aqueous acids. For example, Na2O plus 2 NH4Cl in liquid ammonia gives sodium chloride, ammonia and water. Copper oxides plus ammonium chlorides in liquid ammonia gives copper dichloride, ammonia and water. Solution of ammonium halides in liquid ammonia may be used as acids in the preparation of silane and arsine. Reactions of ammono bases. Ammono base is a substance which in liquid ammonia solution gives NH-2 ion. The commonest base is potassium amide, which is much more soluble than lithium and sodium amides. Metal salts react with ammono bases to give amides, imides and nitrites which get precipitated in liquid ammonia. Precipitation reactions involves double decompositions because of the difference in the solubilities of various substances in water and in liquid ammonia. A large number of precipitation reactions which are normally possible in water have been reported to occur in liquid ammonia. For example, silver chloride is precipitated in aqueous solution. Similarly, a white precipitate of barium chloride is produced when solution of silver chloride and barium nitrate in liquid ammonia are brought together. Lithium chloride may be precipitated by the reaction of ammonium chloride and lithium nitrate in liquid ammonia. Iodides and bromides get precipitated when solutions of various nitrates and ammonia halides in liquid ammonia are mixed together. Many metal sulfides can be precipitated in liquid ammonia by ammonium sulfide from the nitrate solutions of the metals. Ammonolysis. The solvolysis reactions in liquid ammonia are called ammonolysis or ammonolytic reactions. These are analogous to hydrolysis reactions and involves the attachment of ammonium ions or amide ion to the reactant. For example, hydrolysis of SiCl4 occur as SiCl4 plus 4H2O gives silicic acid. Similarly, ammonolysis of SiCl4 may be written as SiCl4 plus ammonia gives tetraamindosilane plus ammonium ion and chloride ion. It may be noted that in ammonolysis, an atom or ion from a substance is replaced by a nitrogen containing ion or radical. When organic halides which undergo slow ammonolysis are ammonolyzed at the boiling point of liquid ammonia, mixtures of primary, secondary, tertiary amines are obtained. For example, Rx plus NH3 gives primary amine and ammonium halide. Alkyl halides plus RNH2 plus ammonia gives secondary amine plus ammonium halide. Alkyl halides plus R2NH plus ammonia gives tertiary amine and ammonium halide. Thus, ammonia molecule is basic and has strong tendency to accept protons and therefore it will act as a base. However, towards are very strong bases, it acts as a proton donor. Examples of type of ammonolysis reactions are sodium hydride plus ammonia gives NaNH2 plus H2. NaCH3 plus NH3 gives NaNH2 plus CH4. Na2O plus 2NH3 gives 2NaNH2 plus water. Complex formation reactions. Many complex formation reactions in liquid ammonia are reported which are similarly to reactions occurring in the aqueous systems. For example, zinc nitrates react with the potassium amide to form insoluble zinc amide which dissolves in excess of amide due to the formation of complex compound of zinc. The reaction is analogous to reaction of zinc nitrate with sodium hydroxides in water. Some other complex reactions in liquid ammonia are CuCl2 plus 4NH3 in liquid ammonia gives a complex of tetraamine copper chloride plus AgCl plus ammonia in liquid ammonia gives AgNH3 twice chlorine. formation of ammoniates. Just as water forms hydrates, ammonia also forms ammoniates with many inorganic salts. In these compounds, the ammonia molecules are coordinated to the cation. Some typical ammoniates are BF3 plus NH3. In liquid ammonia gives BF3.NH3. MgI2 plus 6NH3 in liquid ammonia gives MgI2.6NH3. SiF4 plus 2NH3 in liquid ammonia gives SiF4.2NH3. NiI twice plus 6NH3 in liquid NH3 gives NiI2.6NH3. Redox reactions. Liquid ammonia acts as an excellent medium for redox reactions. In liquid ammonia, the oxidizing actions of strong oxidizing agents is weaker than in water solution. For example, nitric acids in liquid ammonia does not act as oxidizing agent. Similarly, KMnO4 in liquid ammonia act as a very weak oxidizing agents. On the other hand, reducing agents show increased reactivity. For example, alkali metals act as a very powerful reducing agents in liquid ammonia. For example, sodium metal in liquid ammonia reduces cupric iodide to copper, KMnO4 to K2MnO4, etc. Solutions in liquid ammonia. The dielectric constants of liquid ammonia is low, therefore is expected to be a poor solvent for ionic substances. Amongst the inorganic compounds, all ammonium salts, nitrates, thiocyanates, and iodides are soluble in liquid ammonia. Oxides, hydroxides, carbonates, phosphates, sulfates, and most of the sulfides are insoluble. Most fluorides are insoluble in liquid ammonia, and the solubility among halides increases iodine more than bromine, then chlorine, and then fluorine. Most of the iodizes are soluble. Calcium and zinc chloride, which are extremely soluble in water, are quite insoluble in ammonia. Organic compounds such as halogen compounds, alcohols, ketones, esters, simple ethers, phenols, amines, nitro compounds, etc., are readily soluble in liquid ammonia. Aromatic hydrocarbons are sparingly soluble. Paraffins and benzenes are not soluble. Amongst the elements, metals like magnesium, aluminium, zinc, calcium, lanthanide, cerium, manganese, etc., are only slightly soluble in liquid ammonia. Alkali metals and alkali earth metals are highly soluble in liquid ammonia. These forms very interesting solution and are discussed below. Non-metals like sulfur, phosphorus, iodine, selenium are insoluble in liquid ammonia. Solution of alkali metals in liquid ammonia. The most striking property of liquid ammonia is its ability to dissolve alkali metals. The resulting solutions are blue and extremely good electrical conductors. The important characteristics of alkali metal solutions are these are blue in color and the color is independent of the metal dissolved. When the concentration of the metal is increased, the color changes to bronze and shows metallic appearance. These solutions are conducting and show strong reducing properties. These solutions are paramagnetic and paramagnetic characters decreases with increasing concentrations if the reagents are pure and dry. Sodium solutions in liquid ammonia are stable and can be preserved for several days. When alkali metals are dissolved in liquid ammonia, they ionize to give metal ions and valence electrons as sodium ions in liquid ammonia gives sodium ion and electrons. Both the alkali metal ion and electron become solvated by ammonium molecules. Na positive plus XNH3 gives NaNH3X cation or called ammoniated cations. Electrons plus YNH3 gives ammoniated electrons. The completed reactions may be represented as sodium in liquid ammonia gives ammoniated cations and ammoniated electrons. The ammoniated electrons are responsible for blue color of the solution. This is due to the absorption of visible light by ammoniated electrons. The electrical conductance is also due to the ammoniated cations and ammoniated electrons. The conductivity of a metal in liquid ammonia is comparable to that of an aqueous solution of a typical ionic compound. As the concentration of the solution is increased, the ammoniated cations and the electrons associated, resulting in a decrease of conductivity. Very dilute solution of alkali metals in liquid ammonia are metastables and when catalyzed, they undergo decomposition. As the concentration of metal increases, the blue color changes to bronze, and finally the blue color disappears altogether. This is due to the fact that impurities such as iron oxides catalyze the conversion of metal into amide. On evaporating the alkali metal ammonia solutions, alkali metals can be recovered. The strongly reducing characters of these solutions is due to the presence of the readily available electrons. The important applications of alkali metal solution in organic chemistry is the reductions of many functional group and unsaturated compounds. As already studied, the liquid ammonia is a thoroughly studied non-aqueous solvent. Some of its advantages and disadvantages as a solvents are given below. Advantages of liquid ammonia as a solvent. The dissolution of alkali metals without chemical reaction is one of the greatest advantages of using liquid ammonia as a solvent. The dissolved alkali metals can be recovered from the solution by evaporation. The alkali metal solutions are strong reducing agents, even stronger than hydrogens. Ammonium salt dissolved in liquid ammonia acts as amino acids, and this finds applications in preparative chemistry. They can be used to prepare silane, arsine, etc. The tendency for solvolysis is less in liquid ammonia than in water. Disadvantages of liquid ammonia as a solvent. The liquid range for liquid ammonia is from minus 33.3 to 77.7 degrees Celsius. Therefore, a low temperature or high pressure is necessary while working with liquid ammonia. Liquid ammonia has an offensive odor, therefore it requires special techniques to use it as a solvent and as a reaction medium. Liquid ammonia is hygroscopic in nature, and so all the reactions are to be carried out in sealed tubes. Liquid sulfur dioxide. Liquid sulfur dioxide is a non-protonic solvent or aprotic solvent because it does not contain any hydrogen atom. It is also one of the most important non-aqueous solvents and has been widely used in industry. Under normal conditions of temperature and pressure, sulfur dioxide is a gas, but it can be readily liquefied and easily maintained in the liquid phase. It has a wide liquid range and can be used as a solvent. It can be easily purified by passing the gas through sulfuric acid and through P2O5 to remove traces of water. Its dielectric constant is small and therefore is a good solvent for covalent compounds. The characteristic physical properties of liquid sulfur dioxides are given in table 5. Structure of sulfur dioxide molecule. Electron diffraction studies have shown that sulfur dioxide in gaseous phase has the angular structure as shown ahead. The valence bond theory predicts that the SO2 molecules is a resonance hybrid of the following two resonating structures. Solubilities of compounds in liquid sulfur dioxides. Amongst the inorganic compounds, iodides and thiocyanates are most soluble. In case of alkali metal halides, the solubilities are in the order metal iodide, then metal bromide, then metal chloride, and then metal fluoride. The uninegative polyatomic anions such as ClO negative 4, NO negative 3, BF negative 4, etc. are generally more stable in liquid sulfur dioxide. Salts of multi-negative anions such as sulfate, sulfide, oxide, etc. that are practically insoluble. Many of the ammonium, thallium, and mercuric salts are soluble. It is an excellent solvent for covalent compounds. Many covalent substances like halogens, interhalogens, phosphorus halides, oxyhalides of sulfur, phosphorus, etc. and halides are soluble in it. Metals are insoluble in liquid sulfur dioxide. Amongst the organic compounds, aromatic hydrocarbons and alkenes have very high solubility in liquid sulfur dioxide in comparison to saturated hydrocarbons. Pyridine, quinoline, ethers, halogens, derivative, and acid chlorides also dissolve in liquid sulfur dioxide. Many compounds is dissolved in liquid sulfur dioxide due to solvate formation. For example, Ki.4SO2, Cai2.4SO2. Many donor molecules also form stable solvents with SO2. For example, C5H5N SO2, C6H5OCH3. SO2, BF3.SO2, etc. Autoionization of SO2. Pure SO2 is a poor conductor of electricity, though it is believed to autoionize as SO2 positive and SO2 negative 3 ions. The thionyl ion is analogous to the hydronium ion and ammonium ion, and sulfite ion correspond to hydroxyl and amide ions of the aqueous solution ammonia system respectively. Reactions of liquid sulfur dioxides. Some important chemical reactions in liquid sulfur dioxides are discussed below. Acid-base reactions. Liquid sulfur dioxides undergo autoionization as sulfate gives thionyl ion and sulfite ions. According to the solvent system concept of acid and bases, the compounds which gave thionyl ions in solution of SO2 would behave as acids, whereas compounds which gave sulfite ions in liquid SO2 would act as bases. For example, compounds such as SOCl2, SOBr2, etc. act as acids in liquid sulfur dioxides. Thionyl chloride gives SO2 positive and 2 chlorine negative ions. Thionyl bromide acid gives thionyl ions plus bromine ion. On the other hand, cesium sulfates increases the concentration of sulfite ion and therefore behave as a base. Typical acid-base or neutralization reactions in liquid SO2 may be written as SOCl2 plus CS2 SO3 in liquid SO2 gives CSCl plus SO2. SOBr2 plus N bracket to CH34 SO3 liquid SO2 gives 2N CH34 bracket Br plus 2 SO2. Amphoteric behavior is shown by zinc and aluminium ion. For example, AlCl3 react with SO2 negative ions in liquid SO2 to form insoluble aluminium sulfides Al2SO3 thrice. However, if the precipitate is treated with excess of sulfides, the precipitate redissolves. This reaction is analogous to behavior of AlOH3 thrice in bottom. If some acid SOCl2 is added to the soluble complex solutions, the aluminium sulfide reprecipitates. This reaction is also analogous to reactions in bottom. Similarly, sources of zinc show amphoteric behavior in liquid SO2. Solvolytic reactions in liquid sulfur dioxides are not as common as they are in other protonic solvents such as ammonia. Some reactions are given below. Ammonia acetate is solvabilized in liquid SO2. This reaction is analogous to the reaction of ammonia acetate in bottom. Certain covalent halides such as PCl5, PBr5, UCl6, ASCl5, WCl6 undergo solvolysis in liquid SO2 in sealed tube. Many binary halides such as SbCl3, SbCl5, SiCl4, SnCl4, BCl3, SCl2, SCl4, MoCl6, etc. do not undergo solvolysis in liquid sulfur dioxides. The formation of solvents, that is, the addition compounds with the solvent, is also known. Typical examples of solvents are sodium iodide .4SO2, RBI.4SO2, KBr.4SO2, CaI2.4SO2, BaI2.4SO2, SiI2.4SO2, AlCl3.2SO2, etc. Precipitation reactions. A large number of precipitation reactions can be carried out in liquid sulfur dioxides due to selective solubilities of compounds. The precipitates of several insoluble compounds in liquid sulfur dioxides can be carried out by treating them with soluble compounds in sulfur dioxide. Some of these reactions are given below. Thionyl derivatives can be prepared in liquid SO2 by the action of thionyl chloride. 2CH3COOAg plus SOCl2 in liquid sulfur dioxide gives AgCl precipitate and thionyl acetate. Ki plus SOCl2 in liquid sulfur dioxide gives KCl plus SOI2. NH4SCN plus SOCl2 in liquid sulfur dioxide gives NH4Cl SOSCN twice. Complex formation reactions. A large number of complex ion formations in liquid sulfur dioxides have been reported. For examples, the solubility of iodine in liquid sulfur dioxides is greatly increased by the addition of potassium or rubidium iodide. This is due to the formation of the complex Ki3 or RBI3. Similarly, the increase in the solubility of cadmium iodide and the mercuric iodide in liquid sulfur dioxide is attributed to the formation of complexes. CDI2 plus 2KIO gives K2CDI4. HGI2 plus 2KI gives K2HGI4. AlCl3 react with the sulfite ions to form a precipitate of Al2SO3 thrice, which dissolves in excess of sulfite ions, forming the complex ion AlSO3 thrice 3 negative. AlCl3 plus 3SO2 negative 3 gives Al2SO3 thrice plus 6 Cl negative. Similarly, SbCl3 plus KCl gives K3SbCl6, SbCl5 plus KCl gives KSbCl6, SbCl5 plus NoCl gives NoSbCl6, SbCl5 plus CH3CoCl gives CH3CoSbCl6. Organic reactions. A large number of organic reactions have been carried out in liquid sulfur dioxide because organic compounds are soluble in it and it is relatively inert solvent. Some other examples are sulfonation of aromatic hydrocarbons by sulfur trioxides or chlorosulfuric acids. Liquid SO2 has also been used as a solvent for Friedel-Crafts type reaction. In this reaction, AlCl3 is used as a catalyst which is highly soluble in liquid SO2. It is also used as a solvent for the addition and substitution of bromine reactions. Sulfur dioxides or crystallizations. These reactions are also called solvation reactions. Like water and ammonia, salts having sulfur dioxides of recrystallization have also been observed. Some examples of sodium iodide .4SO2, Ki.4SO2, Li.2SO2, Bai2.4SO2, AlCl3.SO2, KCNS.SO2. These are formed with the highly soluble salts and are analogous to hydrates. Redox reactions. Though gaseous sulfur dioxides behave both as oxidizing and as reducing agents, liquid sulfur dioxide does not show any marked reducing or reducing tendency. It simply acts as a medium for certain redox reactions. For example, iodine is liberated from potassium iodide in the presence of SbCl5 in liquid sulfur dioxide. Some special features of liquid SO2 as a solvent. Liquid sulfur dioxide possesses some special advantages over other solvents as a reaction medium. Some of these are: it has low melting point, low boiling point, and these allow it easy evaporation and therefore removal from the reaction mixtures. It has low melting point and therefore it allows reactions to be carried out at low temperatures. Liquid SO2 is an inert solvent. It has an unusual solvating powers for both covalent and electrovalent compounds. It is a better medium for covalent compounds like hydrocarbons and is used for the purification of some petroleum products. It is used as a dilute for the superacid medium, which help in reducing its viscosity without affecting its acidity. Thank you.